In this lesson, we're going to introduce the concept of a real number. The real numbers are quite different to the numeric sets that we've introduced to you so far. To show this, I want to show you this idea of correspondence between numeric sets. I've started by drawing out the natural numbers here, starting at 1, then 2, 3, 4, 5, 6, 7, and so on. As we know, there are an infinite number of natural numbers, because after all, you could continue this pattern more or less forever. You can go to 8, 9, 10, and you could go on as long as you like. So I'm going to start by asking a bit of a strange question. Are there more integers than there are natural numbers? Well, to answer that question, I've just drawn two example sets here. You can see that both of these sets have exactly 3 elements in them, and that means both of them have the same cardinality. To show that the elements have the same cardinality, you can draw arrows between the first set and the second set. If every element in the first set is paired to an element in the second set, then they have the same cardinality. So when we want to compare two sets that are infinitely large, we're really going to need to hinge on this definition of cardinality. We have to say that two sets are going to be equivalent if you can somehow pair every element in the first set with every element in the second set. So therefore, if I can pair every integer with a natural number, then it must be true that the number of natural numbers is equivalent to the number of integers. So I've just written out the first few integers, but they follow a pattern that can show you that there is a very simple pairing between the natural numbers and the integers. We start with the integer 0, then we go to 1 and then minus 1, then 2, then minus 2, and 3 and minus 3, then 4 and minus 4, and so on. Well, in this case, we can say that 1 pairs up with the number 0, 2 pairs up with 1, 3 pairs with minus 1, 4 pairs with 2, and so on. And therefore, in that case, we can say that the first integer is 0, the second integer is 1, and then the third integer is minus 1, and so on. Now, as we said, if you compare the elements from the input set to every element in the output set without missing any elements, then you have to say that the two sets must be the same size. Now, because there's a pairing between every natural number and every integer, then it must be true that the natural numbers are the same size as the integers. So because we've established a pairing between the natural numbers and integers, they must have the exact same cardinality. But then we can ask the same question for the set of rational numbers. If we include the rational numbers, are there more rational numbers than there are integers? Now, just to remind you, a rational number is basically any number you can write as a fraction, like 2 over 7. But the only condition is that the numbers on the top and the bottom have to be coprime, or in other words, they can't have any common factors. So the real question is there any possible way to list every single rational number in some order where you don't miss any rational numbers whatsoever? Initially, it seems like that's a bit of an impossible thing to do. But let me show you a way where it actually can be done. So to make this clear, we want to list all of the rational numbers out in some order, any order, where none are left out whatsoever. To help you understand what I'm about to do, anything written in the form a over b, where a and b are two integers, will always be inside of the set of rational numbers. So therefore, to make every possible rational number, you just need to list out every possible numerator and every possible denominator in a giant grid. So I'll make the numerators run across, and I'll make the denominators run down, as I've shown you here. So to show you this, the first number that's going to go over here is going to have a numerator of 1 and a denominator of 1, so it's going to be 1 over 1. After this, we have a numerator of 2 and a denominator of 1, so that's going to be the number 2 over 1. Now, just to pick another one at random, to make the idea as clear as possible, I want to pick a numerator of 3 and a denominator of 4. In that case, we'd have the number 3 over 4. Now, at this stage, we might as well fill out the rest of the grid. So let me do that in fast motion. Now, since going left drops the numerator by 1, and going up drops the denominator by 1, then if you go left and up from here, this is technically 0 over 0. But remember that dividing anything by 0 is a big no-no, so we have to make sure we don't include this number. However, in this list, we are never actually going to have the number 0. So we should instead over here add the number 0 over 1. Now of course, both the numerator and the denominator can keep getting bigger, so we can continue this list as far as we like. Now after this, we technically need to go on a crossing spree as well. I want you to realize that lots of numbers are repeated on this list. For example, 2 over 2 is the same thing as 1 over 1. 3 over 3 is also the same thing as 1 over 1, and so is 4 over 4 and 5 over 5. There's actually a really easy and interesting way to discover duplicates on this list. If we start up at 0 over 0, we move to the right by 1 and down by 1 to get 1 over 1. That means every time you repeat this motion, you're going to get a duplicate. So moving right by 1 and down by 1 gets you 2 over 2, which is a duplicate. Doing it again gets you 3 over 3, and that's another duplicate. But then of course you can apply that to any number. So for example, if we move to the right by 1 and down by 2, we get to 1 over 2. If we do it again, moving right by 1 and down by 2, that's going to give us 2 over 4. 2 over 4 is of course the same thing as 1 over 2. Now of course, you could use this technique to get more duplicates as well. So for example, if we went down by 1 and to the right by 2, then we get 2 over 1. Going down by 1 and right by 2 again gets you to 4 over 2, which is the same thing as the number 2 over 1. But now you're probably wondering how we can use this grid to actually write these out in a particular order. And all you need to do is to just make up some pattern and then write everything out in that order. For example, I could start up here and then move left, and then I could keep moving left in diagonals, and every time I see one that's been repeated, I just don't include it. So, in the pattern I've chosen, we start with 0 over 1 and copy that down. Then we start by going through these diagonals. So the first number we see is 1 over 1, and we copy that down here. Now, after 1 over 1, we also include its negative so we don't miss any of the negative numbers. But then once we finish this diagonal, we continue down this diagonal. The next number would be 2 over 1, so we include it and its negative. The number after that is 1 over 2, so we include that and its negative. If we were to continue, the next number we'd see is 3 over 1, so we include 3 over 1 and its negative. Then we see 1 over 3, so we include 1 over 3 and its negative. And then 4 over 1 and 3 over 2, and so on. Now there's nothing special about this particular pattern. You could have just started here and then you could zigzag through the numbers like this if you like. It doesn't really matter how you do it, as long as you don't miss any of the numbers. But I hope you can see that by doing this, we will eventually get to every single rational number that could ever exist, and we're never going to miss a single one. And therefore, we come to this interesting and quite unexpected conclusion. Since you can pair every integer with a rational number, that must mean there are the same number of integers as there are rational numbers, and also the same number of rational numbers as there are natural numbers. Now, this might actually not feel right to you, because you would think that since there are these numbers over here that don't appear in this set, surely this set is larger than this set, right? But one thing you're missing when making an argument like that is that these sets are infinite sets. They literally go on forever. So the whole idea is that because these sets are both infinite, they are going to have the exact same size, and that size is infinity, I suppose. Now, saying that these sets all have infinite cardinality is totally fine, but the symbol we usually use is not this infinity sign, but another one that looks a little bit fancier. The symbol we usually use is this one over here, which is called Aleph No, but you should just think of it as infinity. Now before continuing, I just want you to understand that this is not the only way to actually list out the rational numbers. There are many other techniques out there, including the Pairings sequence and a bunch of others. But this is just one possibility to get us started. I'm not going to talk about the Pairings sequence in this particular video, but I will do another video on it very soon, and it is very interesting. I just want you to understand that there are many ways that you can actually list out the set of rational numbers. But now that you've seen that these three sets have the same size, we're finally ready to see the main difference between them and the real numbers that we came here to see. I'm going to go right out and say it here. It is impossible, totally impossible, to find any pairing between the natural numbers and the real numbers that includes every single real number. Now, this is actually a really strange thought, and I'll forgive you if it doesn't make sense to you right away. But we're saying that all of these sets have the exact same size, because they're all infinite sets. But somehow we're saying that it's impossible to actually find any pairing between these sets and the real numbers. and not just the real numbers, but any subset of the real numbers. Now, a crazy claim like this actually needs a crazy proof. So that means I'm going to need to explain to you why it is impossible to actually pair up everything from here to everything on the right hand side. Now, just as we discussed in our lesson introducing all the numeric sets, the main difference between a rational number and a real number like this one is the presence of this ... right at the end. For any rational number, if you wrote out the decimal expansion, at some point you will start to see a period, or in other words a repetition of the digits. For a real number, however, this ... or this ellipsis actually tells us that we need to continue finding digits for the rest of eternity. This idea that you need to keep finding digits forever is actually the reason why real numbers are so strange. So I want you to imagine that somebody comes to you and tells you that they've found some way to pair the natural numbers up to the real numbers. And these real numbers are all going to be numbers between 0 and 1. So we're not going to have any smaller than 0, and we're not going to have any bigger than 1. Now, just like we did for the rational numbers, whoever gave you this list came up with some clever way to generate them in some order. So I guess the only question is it possible for this list to contain every single number if you were to keep going forever? Or is it also possible to say that there must be some numbers that do not appear in this list? If we allow ourselves to think of real numbers as numbers that continue on forever, then it's very easy to show that there must be some numbers at least missing from this list. Now, aside from just telling you that it's impossible, I can actually find a number that is guaranteed to not belong to this list. And the argument comes from a really smart dude known as George Cantor. The argument is actually pretty simple. For the first number, just take the first number after the decimal. For the second number, take the second number after the decimal. For the third, take the third number. And the fourth, take the fourth number, and so on. If we construct a new number that's different in all of these digits, then the new number must be different to every single number on this list by at least one digit. To show you this, let me actually construct a number like this, and I'll explain. Now, the argument here is that this number that I've just added to the list could not have been on the original list. In other words, it does not appear anywhere in this pairing whatsoever. The way I constructed this number is I took every single digit and then raised it by 1, and if I had a 9, I just made it 0. So for example, the 3 turned into a 4, the 9 turned into a 0, the 8 turned into a 9, the 6 turned into a 7, and the 1 turned into a 2. Now you could have constructed this number in many other ways, but I can guarantee you that this number could not have been on the original list, for one simple reason. This number could not have been the first number, because it's different in the first digit. This number also couldn't be the second number because it's different in the second digit. It can't be the third number because it's different in the third digit. It can't be the fourth number because it's different in the fourth digit. It also can't be the fifth number because it's different in the fifth digit. And you could just continue doing this. It's not the sixth number, it's not the seventh, or the eighth, or the ninth, or any. Now, your friend started off by telling you that they have some pairing between the natural numbers and the real numbers. But because you were able to find at least one number that's not on their list, then it's actually impossible for them to hand you a list that contains a pairing between the natural numbers and every real number. And I guess that makes sense if you think about it for a moment, because not only are we allowed to go to infinity this way, but every single number can also go to infinity this way as well, which is not allowed in the natural numbers, integers, or the rational numbers. Because it's impossible to establish a correspondence between the natural numbers and the real numbers, some people actually say that the real numbers are larger than all of these sets. And if you think about that, it's a bit of a funny thought, because we're saying that you have some infinity that's bigger than these infinities over here. Sets like the real numbers have a bunch of interesting names as well. We can call them uncountable sets or unlistable sets, but the basic idea is that it's impossible to write down any list whatsoever that contains all of them. But then that kind of calls into question whether or not it's even possible to write down a real number in the first place. So let me show you a real number that's pretty famous, which is the square root of 2. Now, the square root of 2 is a prototypical example of a real number, and it occurs somewhere between 1 and 2. Now, I want you to imagine that we wrote out the digits for the square root of 2. We can say that the square root of 2 is approximately equal to 1.41421 ... or ellipsis, or whatever you want to call it. But the general idea is that this ... doesn't actually tell us how to find, say, the 50th digit or the 60th digit. In a sense, it's just a promise that if I wanted to, I could write more digits. Now, the square root of 2 is approximately equal to 1.41421 ... or ellipsis, or whatever you want to call it. Now, by writing the number out in this format and putting this ... at the end, we don't actually have any way to calculate, say, the 60th digit or the 70th digit. In a sense, this ellipsis at the end just gives you a promise that you could calculate more digits if you spent more time. If you actually ever wanted to write down the square root of 2 as an exact value, you would need an infinite number of digits. And that's actually absurd. How could you ever write down an infinite number of digits? In fact, it's funny that you mention that. We actually call these numbers surds. And the whole idea is that surd sounds a little bit like absurd. That's because they come from the same word. The suffix surd means that something is crazy or that it can never be done. Now, despite the fact that numbers like the square root of 2 are absurd, we can actually do maths with them just fine. There's nothing wrong with actually using the square root of 2 as a number and computing with it. In a sense, you can think of the square root of 2 as a cut. To give you the exact name, we'd call it a dedekind cut. And the square root of 2 cuts the number line into two parts, the left part and the right part. You can think of root 2 as a pair of sets. The one on the left is going to be called L, and the one on the right is going to be called R. Now, the whole idea of the square root of 2 is that it shows up as the hypotenuse of a 1 by 1 triangle. Now, because of Pythagoras' theorem, 1 squared plus 1 squared has to be the same thing as root 2 squared. And then 1 squared plus 1 squared is just 2. So the whole idea behind root 2 is that it's going to be the number that squares to give you the number 2. But as we know, there's no such number that will ever do that. So therefore, you can think of the left set as the set of numbers that square to give you a number that's less than 2. And then the right set can be thought of as the set of numbers that square to give you a number that's actually greater than 2. We can easily write this in terms of the set builder notation that we introduced in an earlier lesson. So to make this really clear to you, this set on the left here, which we call L, is the set of real numbers such that x squared is actually less than the number 2. So for example, if you think of the number 0, 0 squared is going to be the same thing as 0, and that means 0 squared is less than 2, so it is in the left set. 1 squared is actually going to be 1, and that's also less than 2, so it's also in the left set. On the other hand, the number 2 is not in the left set, and you can see this really easily because 2 squared is actually 4, and 4 is not less than 2, so this one actually ends up in the right set. So therefore, as you can see from this condition over here, the square root of 2 cuts the real number line into two parts, and the one on the left is called the left set, and the one on the right is just called the right set. Actually writing out this left and right set is not really that important, but I want you to just understand that they make a cut and break the set up into two parts. So therefore, I'd just like to summarize everything we talked about in this lesson. In this lesson, we said that two sets have the same cardinality if you can make a pairing between the elements in the first set and the elements in the second set. From this, we were able to show that the natural numbers, the integers, and the rational numbers all have the exact same cardinality, and mathematicians call this cardinality Aleph Null. On the other hand, we said that it was impossible to find any possible pairing between the natural numbers and the real numbers. Any possible pairing must be missing at least one number. Because of this really weird behavior, the real numbers have a very different behavior to these three types of sets that we discussed at the beginning. To explain this, we looked at a particular real number, which is the square root of 2, which shows up when you're studying Pythagoras' theorem. We said that the square root of 2 can be approximated as 1.41421 and then this ... over here. The whole idea is that this ... does not actually tell us how to calculate the next digit. It's just the promise that if we had more time, we could calculate more digits. In fact, in a future lesson, I'll actually show you how to calculate more and more digits of numbers like the square root of 2. We'll also explain exactly where the square root of 2 comes from in much more detail than I did in this lesson. I was very brief about it here, but I'll explain it in much more detail later. But because of this, we said that writing out a number that has an infinite number of digits is absurd, and that's actually the reason people name these surds. But you can think of numbers like this as dividing the set or the real number line into two parts, the left part and the right part. To be straightforward, there are lots more numbers out there that also qualify as real numbers, but they're a little bit more complicated than the square root of 2. Now, surds are actually reasonably simple real numbers, because they can be defined by a really simple condition, like this one over here. Now, as far as real numbers are concerned, the square root of 2 actually has a really clean and reasonably simple definition. There is actually another whole class of numbers, called transcendental numbers, that are actually much more complicated than the square root of 2. Unlike a surd, the left half of a transcendental number technically needs an infinite number of conditions to define it. However, given any rational number on this real number line, you could always decide whether or not it was actually on the left or the right in a finite number of steps. I merely mention transcendental numbers here, just so that you've heard about them, but I'll talk about them much more in a later lesson. For now, you should just think of real numbers as numbers that have an infinite number of decimals, and require an infinite number of decimals to properly define them. Some people actually call the real number line the continuum, because if you had a really sharp knife, and you just cut some place at random, you would definitely hit some real number, but you're not guaranteed to hit a rational number. For example, if you cut right at root 2, you would technically miss every single rational number, if it was possible to have a knife that sharp. Now of course, arguments like this are a little bit metaphysical, but that's kind of what the real numbers are. In general, any number you're ever going to encounter in the real world is definitely going to be a rational number. It's impossible to construct a real number in the real world. So for that reason, I find it kind of funny that they called these the real numbers, because any number that's not a rational number actually can't be made in the real world. Now I've said everything I wanted to say about the real numbers for now. If you continue studying mathematics in the future, you'll see more arguments like this one, and more things about the real numbers like these Dedekind cuts. But for now, I just want you to understand that real numbers are just numbers with an infinite number of decimals. I've said that a few times here, but it's really the most important point. But at this point, I think I've said everything that needs to be said about the real numbers for now. As you study more and more mathematics, as I said, you'll see more about them. But for now, this is really all you need to know. So that completes our lesson on the real numbers. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.